In this video, we will derive the OLS estimates with statistical rigor. When we bring statistical flavor, we will talk about random variables, distributions, significance, etc., which we did not mention at all in the linear algebra perspective. In the population, for each possible height, theoretically there will be people with all kinds of weights. Here is our true population regression line, which we do not observe. The amount by which an individual's actual weight deviates from this line is the error term U. Now, there is no systematic way to track these idiosyncratic errors, so we say that the error term is a random variable. And it comes from a distribution. I'm not saying that the error term follows normal distribution. Not yet. To start off, we need a couple of fundamental assumptions about the error term distribution. Assumption 1. Error terms have zero mean. Now, this is hardly any assumption if the equation includes an intercept. Because if the mean of the error term is not zero, then the constant beta 0 in the equation will absorb that. Assumption 2 is that error terms and the variable x are uncorrelated. Now, this is a really important assumption. So in other words, the conditional mean of the error term u given x is same as its unconditional mean, which is 0. It means that if we freeze x, the conditional density of the error terms at each x will also be centered at 0. Do not think that the conditional density is completely the same as the unconditional density. If that was true, then the error term and x will be completely independent, which is a much stronger assumption. We are only saying that the error terms and x have zero correlation, which states that there should be no linear association between x and u. Else it will mess up the statistical properties of parameter estimates. Now we combine these two equations that state that error terms have zero conditional mean. The assumption means that for a given x, the expectation or average of the error term is 0. That means mathematically, for every x, the expected or average y is just beta 0 plus beta 1 times x, which is also given by our regression line. So regression line passes through the mean of y at every x. Now, if there is a new person and the height of the new person is known to us, which is x0, and we want to predict his weight, our best bet would be the average weight that we would expect for such a height. And we can get this from the fitted line, which is also called as the fitted y or y hat. Note that the actual weight of the person is expected weight plus the error term specific to that person, which can be positive or negative. And there is no way for us to know what the error term would be. So the weight of our subject can be above or below the regression line. And therefore there is always an error associated with prediction. We need to do some more groundwork to be able to talk about prediction error. We will do that shortly in another video. Here is another visual for you to understand the population process or the data generating process. Normally, we plot the density in another axis which is different from the axis of the random variable. Picture height and weight in xy plane and density in z-axis. So this is our regression line in green. Now the ones in blue are the distribution of the error terms u, which are centered at 0 for each x, and the ones in white are the distribution of y centered at the regression line. Think of this as if the regression line pushes the distribution of the error by a systematic factor given by beta 0 plus beta 1 times x. Also note that the distribution properties between u and y are the same, only the means are different. That's because the randomness in y given x is purely because of the randomness in u. Now, as far as estimation of beta coefficients are concerned, the approach is the same, which is minimize residual sum of squares. And the residuals are nothing but the difference between actual values of y and fitted values of y, aka y hat. However, statistical assumptions allow us to build confidence intervals, test significance, and talk about reliability of parameters, which we don't do if we are just doing the algebra or the optimization. Consider a tiny sample of just 3 data points. We have the unobserved true population regression line. From these 3 sample data points, we can estimate our beta coefficients, beta 0 hat and beta 1 hat, say using OLS. Now, if a new sample of 3 data points is drawn from the population, the estimates will change and so will the fitted line. OLS estimates will change every time a random sample is obtained. This is inevitable, but there is a really important concept here. Because sample has randomness and estimates depend on the sample, we have introduced randomness in the estimates as well. It means that the estimates also have a distribution. And we will be able to derive the marginal and joint distribution of the estimates in the next video. That's all for now. Thanks for watching. If you liked the video, please subscribe to this channel to get latest educational content on statistics, finance, risk management, and analytics. Also, if you are a finance professional and looking for a certification in data science, log on to peakstotales.com and check out our prep course for Finance Data Professional, which is a global certification offered by FDP Institute. Experience a new way of learning complex mathematical and statistical concepts with rich visualization in an easy-to-follow Microsoft Excel-based environment. Take advantage of our mind maps and Excel-based hands-on modeling sessions.